Hello, good morning, good evening, good afternoon, everybody, wherever it might be. We're very happy to have another on-site speaker here in Warsaw, all the way from Warwick, England. It's RUDRADIP BISWAS, and he will tell us about some Hopf-Algebra invariants and their relations with each other. So the floor is yours, the Zoom is yours, take it away.
Thank you very much. Thank you for having me. It's my first time in Poland. I'm having a great time. So the invariants that I will talk about are called SILP and SPLE, but before coming to them, I will start with some motivations. There are different ways of motivating the need for or the usefulness of these invariants, and the one that I'm going to go with is the following. So let's say I start with, I have an abelian category. With enough projectives and enough injectives. This.
You cannot write too fast.
Okay. Enough injectives. Am I holding it wrong? At the level of category theory, one can wonder whether starting from an abelian category like this, of course, there are many examples of abelian categories with enough projectives and enough injectives, whether one can get to a triangulated category. Now, usually with starting with an abelian, any abelian category, we can take the derived unbounded category, derived bounded above, bounded below, bounded categories, and those are all examples of triangulated categories. But what if I don't want to take the derived category construction or to do the derived category construction straight away? Is there a way in which I can, starting with A, get to a Frobenius category? Frobenius category. So this is an exact category, again, with enough projectives and enough injectives, with the added condition that the projectives and the injectives are the same objects. Can I get to a Frobenius category and then take the...
Sorry, this is maybe it has a bigger...
Bigger what?
There's one, but
Inertia.
Inertia.
Oh, I see, okay. It's a very precise way of pointing out the problem I was having. Thank you. Yeah, so can we get to a Frobenius category starting with an abelian category? And can we then take its stable category? I will explain what it means right now to quote unquote take the stable category with Frobenius category. So basically, this guy is called F for Frobenius. What I will do is I will take a stable category, I will construct a category such that my objects will be the same as F, will be the same as F. And for arrows, I will just kill everything that factors through a projective injective. And I can say the word projective injective because by definition here, this Frobenius category, the projectives and the injectives coincide. Everything that factors through projective injective. Now, what has this got to do with self or spleen? Well, it turns out if I take my A to be the category of, let's say, KG modules.
Sorry, I have a question.
Yeah.
For this killing, do you assume that category is at least additive?
Yeah, I mean, I start with additive here.
So it was a billion from this class.
Yeah.
Is it a billion, sorry, is additive enough to create this quotient category?
You can create it, but to get it, for it to be a triangulated category, you need a billion.
Okay.
Yeah, you can, well, of course, if it's in create, do the construction. Maybe you can also do it with quasi-abelian, but I don't really know much about quasi-abelian categories. If my A is the category of all, whenever I'm writing big M, it means I'm including all modules, and whenever I'll write small n, in most cases, it will mean I'm talking about finitely generated modules. And in some cases, where the difference matters, finitely presented modules. Or in some other cases where the difference matters even more subtly, the compact objects in the stable module category, but we'll come to that later. So if A is the category of, if A is the category of all modules for a group algebra, now what is A, what is G? So let's say G is, should I write? If G is a finite group, and K is a field whose characteristic divides the order of G. And let's say
Just stop the screen.
let's say I am here, I'm looking at finitely generated modules. Then my mod KG itself is a Frobenius category, and I can do this table category construction straight away. But when G is not a finite group, and this is where basically my talk comes in today. When G is not a finite group, and in place of K, my ring of coefficients is just a commutative ring with some additional properties. For example, let's say I assume additionally that the global dimension of this commutative ring is finite. Can I do this? Not so easily, and that's where self and spleen come in. Let me just add a remark. This looks like a doodle of this. If G is not finite, we can't do this directly. What we can do I erase or do I just click on plus? Plus, right? So what we can do, this is what I will write now, is that we can go to a category called the category of coincident projective objects of A, or the coincident projective modules, if I'm starting with, let's say, big mod plus of small m. I can also start with small m. It's just that I'm being a little bit careful because, as you know, small mod R is abelian if and only if R is coherent, depending on if you're taking left modules and it is left coherent, or if you're taking right modules and right coherent. So sometimes I try to be careful with that. But here we have a finite dimensional algebra, right? So G is a finite group. So one can get to the category of coincident projective modules, which I will define. One can take the stable category, and then you get the stable category associated with the coincident projective modules for infinite groups. And this is what I'll write next. But is that good enough? And why are we doing this? We are doing this in this case to get a stable category. Or a small aim is to get a stable module category of a group.
Stable in what sense?
In this sense.
A stable is just to check equal the projective objects. That's let's say the original motivation for the original term. But and this way one can always construct a stable module category of a finite group. And you can write it, the standard way to write this stabling is with an underline. So one would write mod AG underbar like this. But what about for infinite groups? Can we do this? Not so easily. Well, then can we take the Gaussian projective objects, Gaussian projective modules, take the stable category? Well, yes, that is a triangular category, but is that a good definition or a good candidate for your stable category, for our stable category? That question depends on the self-split factors, which will be the subject matter of my talk today. So let me
I have a question.
Yeah.
So we expect some problems.
Yeah.
Depending on properties, good properties of this category. So my question is, isn't there a way to bypass all these problems by passing straight to the derived category?
Yes, yeah.
And so-
No. Yeah, that is one construction.
Okay.
That is one construction. And a good property expectation is that what the category will get like this has to be triangle equivalent to dB mod kg quotient kb proj or dB proj kg. And that happens for finite groups seamless without any problem. For infinite groups, for that to happen, I need self-split finite. That is the. That is not my theorem. This has been known for a while. Well, while 2019. But yeah, that will be the reason why self-split becomes important.
Okay.
Right. So now what is self and what is spleen? So back in the 80s,
Well, you have an eraser.
No. Activate the pen. Yes.
Yeah, just right. Just
yeah, so back in the 80s, there were two people, Goodrich and Grunberg, who introduced these notions. So Thomas Goodrich and Carl Grunberg, both of them are sadly no longer with us. So self and spleen. So the definitions are done usually for rings, but one can do these definitions for any abelian category within a projective set of injectives where computing projective dimension is well defined. So the L is here because they were using the word length instead of dimension. So self of a ring R is the supremum over the injectors. SILP abbreviation, supremum over the injective length of projectives. But as I said, length means dimension here. Supremum over the injective dimension of projective R modules. I'm just going to write R projectives. Is this too close? Or? Yeah. Yeah. This is silk and spleen. You can see this is very closely connected to, for example, commutative algebra, R being Bernstein. Splee R, but we're not going to say commutative at all in this talk today. Splee R is the supremum over the projective dimension of R injectives. Projective dimension of R injectives.
Please correct me if I'm wrong. When you talk about the either injective or projective dimension, you mean the minimal length of the resolution.
So S refers to
Supremum.
supremum, and il and pli are dual one to each other.
Yes.
Yeah.
It's-
Yeah. Uh, the reason these terms became very useful early on is because of the connection the finiteness of either of them had with the existence of complete resolutions. Now, complete resolutions I'm going to define right now, and this definition is crucial because afterwards I'm going to define Gorenstein projective modules as exactly those modules that can occur as kernels in complete resolutions. I'm doing something wrong with the writing. Sometimes I will write an N and the N won't show up.
But censorship.
Indeed. Indeed, okay. So it was proved in the Great Richmond paper, I'm going to call it GG. It was a proceedings paper. It was a conference proceedings paper from a Singapore conference that happened in 85, but it came out in 87. It was proved that if pli is finite of a ring, then every R module has a complete resolution, which I will define right just now. But admits a complete resolution. Now there is a problem here, and that's why I've left this gap, which I'll write something in that gap after I define what a complete resolution is. So complete resolution, this term has changed meaning somewhat since the 80s. Okay, so R is a ring. R doesn't have to be commutative, but for the sake of sanity, I mean, of course, let's say we are always working with left modules. Whenever I'm saying every R module, I mean every left R module, and I don't even have to take R off. So, so complete resolution, let R be a ring. We say.
Okay, that's interesting.
Oh, I see. You can control the.
I will control you, but I can.
So we take M to be an R module. So complete resolution of M of an R module M is doubly infinite, going to infinity in both directions. Infinite acyclic complex of projectives. Acyclic complex of R projectives. Projectives, which I'm just going to write like this. Let's say P0. So my numbers increase this side. This is, let's say, D0, D minus 1, D1, D2, so on. Doubly infinite acyclic complex of R projectives such that I'm going to write this as
That's a stupid question. Acyclic means that there is no comma.
Such that infinite such that there exists a projective resolution of M that agrees with this guy in high enough degrees. So there exists a projective resolution of M. Let's call this, I've already used P here, so let's call this something like Q. Doesn't have to be finite because I'm not assuming, oh, sorry, I can't do that. Like this, because I'm not, this resolution, the projective resolution of M doesn't have to be finite, because obviously I'm not assuming that M has finite projective dimension. Such that there is a projective resolution of M satisfying so I'm writing this Q star delta star is equal to P star D star. Just write with I. Let's write with I. Qi delta I, this guy, Pi di, they agree in high enough degrees. Or some n. Now, in the 80s, this was the definition of a complete resolution. However, now we will call this a weak complete resolution because we haven't added the total acyclicity condition. This is just acyclicity. The total acyclicity means, is this readable? I meant to write complete. Satisfying this is number A and B. Okay, this I should maybe write B here like this because the second property isn't a property of this projective resolution. But anyway, form between this P star, this complex with, let's say, K is acyclic. Acyclic for any R projective K. Is, how do I? So the second condition is the total acyclicity condition. So in other words, a totally acyclic complex is a double infinite acyclic complex of projectives such that form from that complex to anything projective is acyclic. This is now considered a very standard definition, but it wasn't considered a standard definition in the 80s.
So in particular, if K is equal to R, you have acyclicity of the dual complex. Okay, so this extends acyclicity of the dual.
Yeah.
So this makes it self-dual in a sense.
Yeah.
Okay.
I had never sat down and I knew this, but maybe this was one of the reasons why people realized this had to be added to the definition of complete resolution. I don't know that history. I want to say something extra. Can I have a new color? I can, right?
Wait. I don't understand. It should work.
Maybe first choose pen and then color.
Oh, you're right. Sorry. Yes.
Oh, I see.
First pen,
You're right.
next.
Yeah,
You cannot have a different color of an eraser.
can you give me this? Yes.
Thank you.
Thank you. If B is not satisfied, we add the word weak. As in, we will say weak complete resolutions. What GG showed in 87 essentially is that SPLE is finite and every module has a weak complete resolution. Whether or not that should then imply that every module has a complete resolution is still an open question. But we will come to that in a minute. So this is a neat use of SPLE. And complete resolutions, I will write this in the next, not slide, like the next board. So complete resolutions are to complete cohomology, quote unquote, what normal projective resolutions are to normal cohomology. And complete cohomology is useful in defining the Hom sets in the stable module category that I started talking about at the very start of the talk. So let's move ahead. So remember this definition. And now I'm going to say, let's take R to be a group ring or a group algebra. It's a very original Hopf-Algebra connection here. So if, okay, it's still good. I like blue. If R is a group algebra, so when my group doesn't have to be finite, I'm denoted by gamma, and when it absolutely has to be finite, I'm denoted by.
So these two R's are different.
When it has to be finite, I denoted by G. I think in my paper I write A. Where
A is what?
A
Sorry.
is a commutative ring. A is a commutative ring of coefficients.
No coefficients.
It's a group. Yeah, A is not a good. I mean, it's usually done with.
Because it looks like an algebra to me.
Yeah.
I would change the role of A and R.
Exactly, exactly, because
Yeah, that's right. But before I was writing R modules. Okay.
it's just notation, but it's confusing.
Yeah, it is confusing.
Yes.
S gamma,
No.
sphere spectrum. Okay, I apologize for the bad notation here. Where A is a commutative ring. And gamma any group. Then the term gamma admits complete resolutions, admits or has complete resolutions, means that the true means that the A gamma module A has a complete resolution. Complete resolution over A. Now from here,
What's the action of gamma on A?
gamma on
A gamma module A?
the trivial, trivial.
Trivial action.
Yeah, trivial. Yeah. Yeah, we usually write the trivial A gamma module. Then don't even bother with A. Right. So the A gamma module A has a complete resolution, and I here mean complete resolution as an A gamma module, not as a module over just itself. And from here, we can say all A gamma modules under an extra hypothesis, all.
Not too fast. Try doing this.
All A gamma modules have complete resolution. You can say this if we make the assumption that A has finite global dimension.
I mean, this equivalence holds under this.
Under this assumption. Under this assumption.
Mhm.
Um, have to be gentle with it.
Well, I mean, just have to acknowledge that the speed of light is finite and you cannot go.
So that's right.
Here, this is heavier.
Yeah.
You disallows him to write
Let's
fast.
for the next vote, yeah, let's see. This is actually quite, yeah, right. This is actually quite a non-trivial theorem, and it's quite new, like in this very general form without an Arrhenian condition. This is due to two people, Ioannis Emanuel and Olympia Teleli from Athens.
Ioannis Emanuel?
Yeah.
He's a friend of mine from Berkeley. We studied.
Oh, I see, okay, yeah, that's good. He will come up a lot in this term.
Excellent. He's an excellent mathematician. And he was a student of Wojcicki, right?
Indeed.
Perfect.
Yeah. Not many people have this kind of name recognition with him because since he's been back to Athens. Yeah, anyway. Yeah, he will come up a lot.
Excellent.
If I can write a little faster, maybe. This is 2018. In absolute generality. The actual result involves using the words self and splee, but I'm not doing it just now, just for the terms. So now I left everyone with this result with splee, that if splee was finite, then all modules would have weak complete resolutions. But what about self? Well, if self is finite, then all modules have weak complete injective resolution. So when I'm writing complete resolutions today in this talk, since, as you might remember, the constituent modules in my resolution were projective, some people call these guys complete projective resolutions. And you can do a dual thing with injectives. You then say, use the word complete injective resolutions. So if self is finite for a ring, all our modules have weak complete injective resolutions. I'm not going to do all those definitions, except I'm going to now state a very important result, which was proved in the original Get-Rich-Grunberg paper under an Arrhenian assumption. And as I promised in the abstract, quite a lot of people since the mid-80s have tried to completely get rid of this Arrhenian assumption. And this result is about a very neat connection between self and splee. I'm going to, in the abstract, I wrote the original version for Hopf-Algebras, but since I'm already into group algebras in this talk, I'm going to write it for group algebras.
Sorry, would you do me a favor, please?
Yeah.
I would like to go back to the previous slide or Blackboard. Oh, you skipped number 3. You don't like number 3? Number 3 is empty.
Maybe I pressed it once.
Okay. Just please help me out. I would like to see the difference between the definition of this complete resolution for a group and for a ring. This is what confuses me
A
because
complete resolution for a group is a complete resolution
of a group ring.
over the group ring of the trivial module.
Okay,
Yeah, that's what I was trying to.
okay. Okay, so it's somehow defined.
Exactly, yeah, that's the definition. Sorry.
Okay, I thought it was a statement. Sorry. Thank you so much. Now I'm happy. Yeah, thank you for clearing it out for me. Yeah.
I must say, I have given talks on complete resolution so many times. Never have I had such a mindful audience.
We take it as a compliment.
Yeah, of course, yeah. Okay. Get-Rich and Grunberg. Just wrote GG, I could have just written GG here, anyway. 85, or was I writing 87?
87.
Yeah, so they showed, so A is a commutative ring, A is now Noetherian. Is everyone fine with the use with the term global dimension? So it means there is a supremum, a finite supremum, finite bound on the projective dimension of all A modules, all A modules.
Hence globality.
Yeah. So I assume A is Noetherian commutative. Yeah. And I assume that the global dimension of A is finite and is equal to T. Then for any group gamma, Goodrich and Grunberg showed that self A gamma is actually smaller than equal to, some people write, I should write, put the brackets on, right? Is smaller than equal to splee A gamma plus T. I haven't given this talk in a while, so let me just, there is no way I would make a mistake in this splee location here. I just want to check. I used to speak about it. So smaller than equal to splee plus. Yeah, that sounds reasonable. Just 1 second.
So this means that the difference between silp and splee
Yeah,
must have some meaning.
must have some meaning. Conjecturally, it should be 0 for group algebras. I'll come to that's what I'm coming to. And I proved that it is 0 for a large class of group algebras. And Ioannis and Olympia had proved it also. Olympia had proved it also, and Ioannis and Olympia. Silp is. Why can't I find this exact result? Okay, this is funny, but I'm pretty sure this is correct. Okay, so can we get rid of the Noetherian condition? In the proof, the Noetherian condition was just it was like an artifact of the proof. There was an arbitrary direct sum of injectives that had to be injective for the proof to go through in the original version, and
Is this proof inductive?
no. From what I remember.
Why Noetherian plays a role?
I mean, I don't recall the original proof exactly, but there was a direct sum of A injectives that had to be injective.
Ah, yeah.
Okay, so now can we get rid of Noetherian? So some of the motivating questions for the rest of the talk. Can we remove Noetherian? No. Number 1 and number 2. Are silp and splee always equal when they're, I mean, it is known that they are equal when they are both finite. But how widely is this true? Let's say for group algebras. I mean, the point is usually you can check, well, it's hard. I mean, this is a little disingenuous to say maybe. In some cases, one can compute silp and splee reasonably easily, even with some very bizarre group algebras. And if you can compute only one of them, but the other one is not so easy to compute, then a result like this can help. A result like this can also help.
Sorry, by group algebra, you mean that A is equal to the shield?
No. Group algebra. I should just say group ring.
Group
I
ring.
should just say group ring.
Okay.
I mean something like this.
Okay.
Exactly like this. That's a very, very good point.
No, but in this case, when
Yeah. I mean group ring.
group ring, okay.
Right. So now comes, so I've defined complete resolutions before. And as an aside here, let me just define this word, Gorenstein projective. Gorenstein projective R module. The definition is just that these guys occur as kernels in complete resolutions. In non-weak complete resolutions, mind you. If we're talking about weak complete resolutions, then we can say weak Gorenstein projective. Now, this class of Gorenstein projectives has many interesting properties. For example, almost all of the standard homological tricks that one can perform with projective resolutions or with projective modules can be similarly performed with Goranson projective resolutions and Goranson projective modules. And
Sorry, I'm a bit confused. You say kernels in complete resolution, and we have a resolution and what's an exact sequence of a kernel.
So kernels are equal to co-kernels.
Yeah, so why call it kernels, not just elements?
Kernels or co-kernels.
kernels,
Okay,
Kernels is a shorter
of
word.
course.
as a cycle in a.
Yeah, okay, so we're just, when you have your resolution, you have these elements.
Yeah, the thing is, I mean, I'm using the word resolution more than acyclic complexes. A more standard way to say is kernels in totally acyclic complexes. That just does it. Because when you say complete resolution, it implies that there is a module somewhere in the background whose complete resolution is,
Yeah.
whose
Yes,
complete resolution is entering the picture. So I can just say.
but at this point, it would really help me big time to see an example of something which is projective but not Gorenstein.
Projectives are always Goranson projective.
Yes.
The other way around, it doesn't. Okay.
Okay. So,
So Goranson projective has projective dimension either 0 or infinite.
So Gorenstein modifies the notion of projectivity.
but when you write this resolution, it doesn't have to be a resolution by projectives, by assumption.
Yeah, but
It can be.
kernels of maps between projectives.
Ah, I've got it now. Okay, so this was my original confusion. Okay, thank you so much. Yes, now I understand it.
I'm
Thank you.
looking at kernels in that.
I got it. Thanks.
Kernels in totally. Acyclic complexes. If you want to not even use the word complexes or totally acyclic, there is an X definition that one can do.
Sorry, I'm confused. So adding this completeness to the definition of this resolution is irrelevant.
It is irrelevant for now, but the word complete comes from complete cohomology, and that has to do with complete cohomology of modules. Yeah, but since I've already defined complete resolutions and since they will be used later on for simplicity, I was just defining Goranson projective modules as kernels in complete resolutions of our modules.
By totally acyclic, you mean?
Yes, so totally acyclic was board number 2. Was that extra condition?
This is, oh yes, totally, okay, acyclicity.
Right, okay. Okay, let's move. Can I delete board number 3 somehow?
No, like.
Right. Right. So before, let me. There are several directions one can take. I mentioned Emanuele and Taleli. So remember this question about whether or not Gorenstein projectives, whether or not self and split always satisfied that bound condition without the Noetherian assumption. So Emanuele and Taleli had a very nice result, and that involved the Gorenstein cohomological dimension. So first of all, Gorenstein GPD just means the Gorenstein, I'm writing it red for some reason, Gorenstein projective dimension. This is exactly projective. This is like a projective dimension analog with the Gorenstein projective modules. This can be confusing for representation theoretics and writing small p, it must be finally generated. Let me just write down the full definition. I have already defined the terms. GPD, which is projective dimension, R over R of a module M, is the minimal smallest n such that there exists an exact sequence M G0 G1 Gn, where each of these guys Gorenstein projective. one can replace the class of coincident projective. I mean, there is this word called resolving subcategories, comes from a Swanner, right? And one can do similar definitions for any other class. Instead of say modules come from the constituent modules of your resolution come from coincident projectives, it will say they come from that class. Now,
Sorry, I have a question. So the notion of the projective dimension relies on the fact that projective objects satisfy very good properties.
all of the
What about Gorentz?
all of the analogous properties are satisfied here. Like there's an analogous Schoenwell's lemma. There are analogous properties with the X vanishing condition for finite crest projective dimension. All of these are known.
So there's really a deeper analog of being Gorentz projective.
Yeah. All of these are known. This is a very good question. All of these are known. I don't know how long they have been known for, but most of us just cite this paper by Henrik Holm from 2004. That does all of these things in very lot of detail. He wrote this paper when he was a PhD student, I believe, and it has like 1,000 citations. Standard place to cite for everything. So now, as you might remember, cohomological dimension. So cohomological dimension of, let's say, a group over a ring A is defined as the projective dimension of A as an A gamma module. Similarly, the Gorenstein cohomological dimension of a group with respect to commutative ring A is defined as the Gorenstein projective dimension of A as an A gamma module. Why am I telling you about Gorenstein projective dimension? Gorenstein cohomological dimension? Well, the result by Teleli and Immanuel that I wanted to mention just now gives us a very nice connection between the Gorenstein cohomological dimension and the Sylvan-Splee invariance. So that connection is given in the following way. Let A be commutative ring, again, finite global dimension. And this is a group, any discrete group. Then Sylv and Splee are both bounded by the Gorenstein cohomological dimension plus this global dimension. So this is a theorem of Immanuel and Teleli from 2018. This is interesting because when I was doing work on this thing, I hadn't seen this paper, and for some reason, Jonas doesn't like to put his papers on the archive. So I didn't see this paper until it was actually published in the journal. So I had a proof of this exact same result with an extra condition that this group belonged to a large class of groups called the Kropp-Holler's hierarchy. But that class of groups is,
Sorry, which kind of hierarchy?
It's called Kropp-Holler's hierarchy. It's named after a mathematician called Peter Kropp-Holler.
Okay.
Yeah. For all practical examples, if this result is proved for groups belonging to that hierarchy, we are fine. But we will come to that again in a minute. So until now, I have defined 3 invariants. I've defined GCD, I've defined Sylv, and I've defined Splee. So, and I've already told you that there is a connection between complete cohomology and morphisms in the Hom sets in the stable category. So what I'm going to do now is I'm going to first tell you a neater looking connection between, actually no, it follows from here. So what I'm going to do now is I'm going to give you the good behavior definition of a stable category. And then I will talk about my original contributions to this project, to this question of the relationship between Sylv, Splee, and other invariants. And for that second part, I'll have to define quite a few new invariants, and I will say how they will all be related to each other in a very neat way. Again, obviously, without any hidden assumptions on my ring of coefficients A. Right. I think I'll have to just go to the 20 is the upper bound, right?
Yeah.
Okay. So, first of all, let me define complete cohomology. This definition in this form, speech into 645. Is that right?
Yes.
Yeah. X hat R, so the hat is for complete. And let's say I'm doing everything over A gamma. This A looks like a lot of, A looks a bit like this X, but M, comma, N. M and N are A gamma modules. So by definition, originally there were quite a few contrasting candidates for these X hat groups. Deleted everything. But now we know that they are all the same. They're all equivalent. By definition, it is the limit I tends to infinity over Hom underbound. So this Hom is a stable Hom. So by stable Hom, I just mean I'm killing everything that quotients that factors to a projective, not projective injective, just projective. I'll write it here once I've finished writing this. Stable Hom between stable Hom in A gamma, let's say, or mod A gamma, between this is the G, so I plus R M and I N. To define a few things here. So what is this omega sign? Well, let's say we are in the standard abelian category of A gamma modules. Then we know, this is a Schoenwell's lemma, of course, that if I have a short exact sequence that looks like this, let's say P0 to M, then K0 to P, like this, and P1 to M, and then K1 to P. It's a very, very old and extremely standardized result called Schoenwell's lemma. Schoenwell's, I think it's correct. It basically says that P0 plus K1 is the same as K0 plus P1. P0 plus is the same as essentially, I mean, the reason I'm saying this lemma, or the reason I'm stating this lemma so completely is that, like, don't think there's any funny business going on here, because I'm taking maps between these syzygies, because one can say, what is your choice of this map, or of this guy? It doesn't really matter because of Schoenwell's lemma, and because I'm quotienting out everything that is.
So this means that K1 and K0 are stably equivalent.
I would say, no, P0 and P1. Sorry, K0 and K1.
Okay.
K0 and K1 are stably isomorphic in the stable category, absolutely. And yeah, so I mean, another way in which one can say complete resolution.
Yes, but what's the meaning of this omega, this loop?
Oh, yeah. Oh, I see. This is standard term sometimes for, you know, the kernel. Yeah.
For this class.
Yeah.
Of base.
Yeah. This is well, I say standard term, but I mean, I have spoken in front of homotopy theorists who said they knew this result, but they didn't know the term Schoenwell's lemma. So it's it can be quite complicated in both ways. So when we define the triangulated category structure on the stable category, the expectation is syzygy inverse will be the suspension functor of the triangulated category. I'm not going to write this because I'll have to say quite a lot of other things. And the complete resolution precisely gives me a syzygy inverse and a functor. Precisely gives me a syzygy inverse. You have to keep in mind here that omega 0 m and m, these are stably isomorphic in the stable category. So I can, and since I have a double infinite totally acyclic complex, just acyclic is good enough for this definition, I can go to the right as well as to the left. So I can get omega minus 1, omega minus r. It is.
So this means that stably, there is no difference between something like omega spectrum and the suspension spectrum in stable homotopy theory.
That would be the expectation. In stable homotopy theory, I'm not, like, tautologically, that should be the expectation, but I'm not sure. Yeah, I don't know too many stable homotopy theory examples. Yeah. Anyway, so X hat R, so this is the complete cohomology. Cohomology. One thing to note is that this definition is possible without the aid of complete resolutions. Of course, if you have complete resolutions, you can make this definition more easily. However, again, this is where the next diagram will become important. If you don't have complete resolutions, this category that I'm going to write down now. So I'm writing a category, I'm calling it stab. Stab, big S, A gamma. I don't yet have any conditions on gamma. Gamma is any discrete group. And on A, on A as well, I don't have any conditions just now. So what is this category? So the objects of I think it's time for me to listen to it. The objects are all A gamma modules. All A gamma modules. And the morphisms are given by X hat 0. There's a drag. There is a drag. Yeah, X hat 0.
Classes modulo. Table.
There are classes, right, like this, there are classes modulo maps that quotient through modules with finite projective dimension, because I'm taking this limit. For finite groups, I can just build things that are quotienting through projectives. Arrows, can you read arrows? X0, A gamma. This is giving me my home set. So now, fine, let us call this the stable category candidate. But is this equivalent to the other candidate I mentioned before? So let me just take the full theorem now. From here, I'm going to look at modules concentrated in degree 0. I'm going to the derived category. Derived category. And I'm taking a Verdier quotient with quantitative category of projectives. Keep in mind, this is not exactly the singularity category, because I have, first of all, big M and big P. And also, I don't really know how good looking this ring is. It's a gamma. So I take this map, modulus considered in degree 0. And then from here, I want to go to the homotopy category of totally acyclic complexes. I've defined totally acyclic complexes before. I'm going to go to the homotopy category of totally acyclic complexes. And what is the map? So now I make the assumption that every module has a complete resolution, and that is guaranteed when SILP and SPLI are both finite. I mean, this is a theorem. I mean, did I mention it? Maybe I mentioned it with GCD, question common dimension, but I will write it down once I've written this. So what is happening is I'm going from here to there by taking complete resolutions of bounded complexes. You can do that when you can do it for any like a single module, you can do it also for bounded complexes. So I take complete resolutions. And this is the part that uses the assumption that taking complete resolutions of every module is possible. I take complete resolutions and I come down to the homotopy category of totally acyclic complexes. This is often written KTAC. I don't need to write that notation.
Sorry, but what about boundedness of this? Because at the beginning, the definition of this complete resolution
Was for a single module.
unbounded complexes.
Yeah. These are truly unbounded complexes.
Okay.
These are unbounded complexes. Maybe that's why writing this is useful. This is often written like this: K, T, A, C, totally acyclic complexes.
I don't understand. What is the meaning of this? What is this? Is the functor or what is this?
Yes. Like I will.
Bounded to unbounded.
Yeah.
What taking? Okay.
I'm taking a complete resolution.
okay,
of
okay.
A bounded complex. This complete resolution is an unbounded complex.
So you have a finite complex, but to every member of this complex, you apply this
Not
big
exactly
resolution
every,
construction.
not exactly every member. Basically, just like a complex can have a projective resolution. I mean,
It's a total. It's a total.
Yeah, yeah.
So this total is this unbounded.
yeah.
Okay.
So my end result is this unbounded guy. And from this,
Another question. Is this a stable category a hard with respect to some T structure?
of T structure, not necessarily. Not necessarily. Because you would want to put the T structure on here, wouldn't you?
Yeah.
And yeah, not necessarily. Because I mean, the main problem.
In the triangulated category?
Yeah. No, okay, here's the thing. This guy is obviously always a triangular category, like this is the construction. This guy need not be. But let me just erase.
Need not be abelian.
It need not be a triangular category, but it will be a triangular category through this. Let me erase some things and write this more clearly. Can I do this with my hand? Will work, right? Control Lemma can go away now. Oh, I see. No point.
Yeah, the rest is connected component.
Yeah. Not really doing myself a favor by like rubbing my hand like a maniac. Rubbing my hand.
Like pi zero.
Okay, this is, it's not working. Right. So this theorem, I'm essentially stating a theorem here. But first what I'm doing is I'm saying this category is constructible for any group. Obviously, the definition is easy enough. This map is doable still for any group. I'm just taking modulus considered degree 0. This map isn't doable all the time. I need the fact that I can take up the resolutions all the time. And that is an extra assumption. Now, once I'm in the homotopy category of totally acyclic complexes, I want to go.
Have an eraser.
Switch to pen.
I want to go to the stable category of Gorenstein projectives. Remember, Gorenstein projectives is a Frobenius category, and the projective-injective objects of Gorenstein projectives is precisely the projective modules, the projective A gamma modules. So when I quotient out maps that factor through projective-injective objects, I'm essentially quotienting out arrows that factor through a projective A gamma module. And here I'm just taking this. I can take the, and get this notation mixed up. Is it the -1th cocycle or the 0th cocycle? I can take omega 0. And we know that it is going to give me a Gorenstein projective guy, because by definition, Gorenstein projectives are kernels in totally acyclic complexes. So this is often written like this: G proj A gamma, and then we do an underline. The underline means I'm taking the stable category. And then from here to here, I just take the inclusion. Now, this map, and this map are always possible. At least you can visualize what this map could be.
Sorry, by inclusion, you mean what? Faithfully?
Inclusion of the objects.
Inclusion on objects?
Yeah, on objects, yeah.
What about morphisms?
I mean, it's a full subcategory of.
Full subcategory, okay, good.
Yeah. So, it's a full subcategory of mod A gamma, isn't it? Yeah. G proj is a full subcategory mod A gamma, yeah. Now, these are very good questions. So now this is the only part where I need an extra condition. So the point is, when this extra condition is satisfied, i.e., so if GCD of my group is finite, or equivalently, still A gamma, comma, both of them are finite. Now I'm including the assumption that global dimension of A is finite. Then I get an equivalence of triangulated categories.
You wrote a bound of both silver and P in terms of global dimension and this corresponding.
No. This is equivalent to this
Or
when global dimension A is finite. Yeah. So I'm saying I take one of these equivalent assumptions to begin with, and under that assumption, I get this for free.
okay.
And then this gives me an equivalence of triangulated categories. Yeah. So the fact that these are equivalent for
Opposites.
for any commutative ring of finite global dimension, that is Emmanuel-Taleli.
Very interesting.
So that is Emmanuel, Ioannis Emmanuel and Olympia Taleli from 2018.
Yes.
And the fact that you, like this, do get like this commutative, not a commutative square, what should I say? Like this, you get this equivalence of 4 candidates of this stable module category is due to Matza and Simons. Simons was my PhD supervisor. Let me just write here. Matza, Nadia Matza, and Peter Simons. The paper came out in 2019 in advances, but I believe they were giving talks on it 2016 onwards. However, I don't want to. I've been recorded, aren't I? They proved this result for type 5 groups. So type 5 groups I'll define in a minute. So type 5 groups, so a group is of type 5 over A. This is the definition due to Taleli. A group is of type 5 over A. If for any A gamma module M has finite projective dimension as an A gamma module, if and only if it has finite projective dimension over all finite subgroups. This is the definition of type 5 groups. But the only part where they needed type 5 groups was here to say that, okay, we can take complete resolutions. And they also said Noetherian for, they also used the assumption Noetherian for A, because this paper actually came before Emmanuel-Taleli paper. So they couldn't really use the full force of ET18. This is funny because 18 comes before 19 of us, but I mean, Emmanuel and his collaborators often don't put their papers anywhere until it is out in a journal or until he sends it to you. You can't really know what they're working on.
So to be sure, I want to rephrase what you said.
Yeah.
So this means that these 2 stable categories.
4.
4.
Yeah.
But wait a minute. So these are triangulated categories.
Yeah.
These are what, abelian or?
No. All of these are triangulated categories.
Are triangulated.
Yeah. Equivalence of triangulated.
Okay. So by stab you mean the right category of this?
No, stab I mean
Because
all objects, and then for arrows, I'm taking the zero and complete cohomology group. It is not an abelian category with those.
yes, but is it triangulated? Why?
Yeah, it is, no, that is part of this proof, essentially. It is not always triangulated. It is triangulated.
So it's a part of, it's a claim.
Yeah, it is not always triangulated.
It is triangulated.
Yeah.
Okay, good.
It is not always triangulated. That's a good point.
But it's not defined as the right category.
No.
Triangulated category, not coming from.
Not coming from a derived category or a homotopy category is strange, obviously.
Okay.
But yeah, but here, as I was saying before, the 3 other candidates are naturally triangulated. The constructions involve triangulated categories. Here I'm taking stable category, Frobenius category. Here I'm taking a homotopy category. Here I'm taking Verdier quotient of 2 triangulated categories. But this guy is not always triangulated. It is triangulated under these assumptions. Yeah. Right. Now, obviously, if A is a field of characteristic P and gamma is G, a finite group such that the order of G is a multiple of P, I get back the standard stable modular category construction. Maths assignments 2019. Yeah, so this is how self and split become a very neat constituent. Although I must say the fact that for type 5, okay, I'll go to type 5 now. But there, I mean, should cite myself somewhere here, but it's a well do it. Now, that was the use, the thing that you saw in the previous board was a use of this self-split terminology in a way that when for a group ring self and split are both finite, I can have these sort of well-behaved stable categories. Although, of course, with stable categories, that's not the end of the story. You would require, you could ask more questions. Are these guys compactly generated? Are these guys rigidly compactly generated? Can one stratify them? As in, can one, quote unquote, let's say, classify?
Compact objects. In this
Yeah, exactly. Like that.
Then this is not known. What are candidates for?
It is, you know, it is known, it will, yeah, there are these things called module objects of type F infinity. And in many cases, they turn out to be the compact objects. But yeah, for example, but it wasn't, it is not known. I think one of Peter Simons' students right now is working on this, and he has been able to show, I've heard that all F infinity modules are, no, all F infinity, so F infinity means any module, well, any module is called F infinity if it admits a projective resolution, where all the constituent projective modules are finitely generated. It is easy enough to show that if a module is F infinity, it has to be compact. But the other way around, I don't know, I haven't seen Greg's proof. You're going to ask something else?
No.
Okay. Right. So self and split, that's a use. Now more on how they are related to each other, because as I said, that old result by Gedrich and Grunberg can still be somewhat stimulating. Like really, you can't get rid of Noetherian. So the rest of the talk, I will talk briefly about two of my theorems where I tackled this question in a very, I guess, head-on way, depending on your.
So we finally passed to some Hopf-Algebras.
Yes, so I mean, essentially,
So far there have been no Hopf.
yeah, the group algebras are
But it's
Hopf-Algebras.
boring.
That is boring indeed. So essentially, one can do this thing called strongly graded G algebras. One can look at skew group algebras. So many of these things can be stated for, what's the word, K projective Hopf-Algebras, where K is a finite self-injective dimension. But the problem comes when you look at things like the Grunstein projective dimension, which depends on a group. Like you need to have a group to, so Grunstein cohomological dimension, which depends on a group.
So if I understand Piotr's question.
Yeah.
The problem is that all this theory is for plain modules in a sense.
Group algebras, yeah, modules over group
Yes.
rings and group.
But for Hopf-Algebras, these modules form a monoidal category.
Yeah.
So this is not present here. Yeah.
It is present in the stratification questions that
Okay.
that I mentioned.
So it's a technicality in the proof. Using this monoidal.
Not exactly. It is a generalization of a proof that was known before for group algebras. One can now do it for co-commutative of algebras with some conditions. And then
The definition of this filtration, we are using this monoidal structure.
yeah. Yeah, it's a certification of localizing tensor ideals. You give a bijection between localizing tensor ideals and subsets of the Balmer spectrum of the compacts in the tensor triangular category. Okay.
I'm also craving for examples.
I was going to give some examples of groups and rings that satisfy these things, but for that I wanted to. Yeah, let me give some.
Okay, 15 minutes.
Yeah. That's good. Yeah. Let me give some, because most of the examples are from groups and how those groups can be satisfied, can be put in these classes or cannot be. Okay. So I'll introduce two classes of groups, and then there will be examples non-examples. Yeah, this is important. Okay. Two classes. On this side, I'm gonna have type phi after the lady. Lily. On this side, I'm gonna have proposals hierarchy that I mentioned before. This definition is easy enough to state. Originally, it was done for Z, but in my work, I do it for commutative, normal commutative rings. So gamma, oh God, what did I do? Gamma is type phi over A if for any A gamma module M, the projective dimension of M is finite. If and only if the projective dimension of M as a module, as a restricted module over any finite subgroup is finite. For all. And the class is denoted by F phi A. Here, let's start with a class of groups X, and I define so there will be a hierarchy here. So I start with H0x. H0x is defined as just X. X is any class of groups that I begin with. And then I say gamma is in H alpha X. Now alpha is any successor ordinal or ordinal. We say gamma is in H alpha X if there exists a finite dimensional contractible CW complex on which gamma acts by permuting cells with self-stabilizers, stabilizers in H alpha minus 1x. And then if alpha is the limit ordinal, alpha is only sorry. Sorry. Alpha is limit ordinal. So make alpha x is just defined the normal way, like I take union over H beta x for all beta strictly smaller than alpha. And Hx is just, let's say, so G is in, writing G, if I write gamma is in Hx, it means gamma is in H alpha x. And LHX, this is the local part. Right. So gamma is in LHX if and only if all finitely generated all finitely generated subgroups are in HX. For examples, H1, so if I take X to be the class of all finite subgroups, all finite groups. H1F, for example, contains the free abelian group of infinite rank, but this rank has to be
What about P groups?
infinite P groups. I don't think they,
No. Finite, basically. Is this class of P groups interesting? Exactly.
not necessarily, but they are interesting afterwards if you want to look at whether or not this like due to this action of gamma on this complex, you get an augmented cellular complex. If you then want to make that complex in addition to, if you want to make that complex mod P acyclic, then having a P group is helpful. And then you can say something about whether the group cohomology ring with mod P coefficients is a Noetherian, like finitely generated. Just one second. Done. Yeah, of rank between 1 and Aleph 0 is in H1F. Between, and if I want a group in H2F and not in H1F, I can take again free abelian group of rank now between Aleph 0 and Aleph omega 0, where omega 0 is the first infinite ordinal. Now, why am I saying all these things? These are examples of groups. You might wonder, like, what is the point here? Well, if a group is in H1F and my ring of coefficients is any commutative ring of finite global dimension, then all modules have complete resolutions. And that is a theorem. I mean, that is not trivial. So if gamma is in H1F, and it is easy enough to show that H1F is actually a subclass of this phi A. If gamma is in H1F and I'm taking A to be of global dimension finite again, then all A gamma modules have complete resolutions. So I can play with this stable category construction at my own will. I mean, very, very happily. For non-examples, usually for type phi, I mean, it is still an open conjecture whether H1F and F phi Z are different. It is known that H1F is always inside F phi Z, but whether the other way around is always true, we don't know. So for non-examples, I'm going to give you some cases where, so there's this group called Richard Thompson's group. Richard Thompson's group that is not in LHF phi A. So if phi A is this class and I'm doing this construction of a hierarchy LHX, now my X is F phi A. Before, so this is actually my result, but before people used to worry mostly about LHF separately and type phi separately. And that was a problem because one used to then ask, okay, can't I have one unified result that will do everything? I haven't defined Richard Thompson group, so let me just say S infinity. It is not Richard Thompson's group, but S infinity contains Richard Thompson's group F as a subgroup. So S infinity is the infinite symmetric group. Infinite symmetric group, for example, is not in this hierarchy. And the proof is somewhat evolved. I'm not going to so about the proof. There are some branch groups. For example, the Grigorchuk group is not in this hierarchy. I'm talking about hierarchy. How about here, but not, how about in the hierarchy, but not in type phi? Well, these guys, free abelian group of rank Aleph 0, rank smaller than or equal to Aleph 0, but strictly bigger than or equal to Aleph 0, but strictly smaller than Aleph omega 0. These groups are not type phi groups, but they are in the hierarchy. which means not all modules can have complete resolutions, but some modules can. Some modules can, but not all modules can have complete resolutions. Let me give one example concretely of, I think this was in my paper again. So if you, so before I was talking about Gorenstein projectives. So here is an example of a Gorenstein projective module, which you can always construct. So any permutation module with finite stabilizers. With finite stabilizers. So one way to just going to write, I mean, if my ambient group is gamma, and I look at this, and G is finite. This result was flourished for a very, very long time, but actually, I think for a neat proof, one has to look at a paper by, I think, Asadullahi, Baleke, Asadullahi, Baleke, and Shakrullah Salarian, 3 people from Isfahan. So most examples are about these groups, and then you choose your A accordingly, and you get cases where the theory fits with all modules or it doesn't fit. Let me, since I don't have too much time left, so let me give the main contribution of mine to the self-free question that I was talking about before. And for that, let me write down the theorem first, and I will explain all the terms shortly. So I take gamma to be a group here, LHF phi A, LHF phi A. And A has finite global dimension. The projective dimension, this is B21, then the projective dimension of this module B gamma A. So what is B gamma A? B gamma A is the module of all gamma to A functions that are only allowed finitely many values.
Finite image, right?
Yeah.
Finite support.
No, not support the image.
No, finite image.
Image, yeah.
Image.
Yeah.
So
Actually, many values. So this guy turns out to be exactly equal to the Gorenstein cohomological dimension. When A is Z, this module is extremely useful. Well, even without Z, this module is extremely useful because it is always A free and it restricts to a free guy over finite subgroups. And all these, I mean, it's always handy to have one concrete module that can detect everything. So let me just, this is, and let's call this guy theta. And there I'm saying they both need not be finite, but I mean, if they are finite, I'm calling them theta. And SILP A gamma ends up being equal to splee A gamma. It ends up being equal to the finitistic dimension of A gamma. I'll define this 2 seconds later. And another quantity called K A gamma. What is the finitistic dimension? So the finitistic dimension, this is a very common quantity from representation theory of finite dimensional algebras, for example, but of course we don't have a finite dimensional algebra here. I take the supremum over the projective dimension of all modules, A gamma, all projective dimension of all modules such that this projective dimension is finite. I take the set of all modules that have finite projective dimension and I take the supremum over their projective dimensions, and K A gamma.
The supremum still can be infinite.
Still can be infinite, yeah. When this is the Thompson group, it is infinite. When this is And that's why those examples from before were helpful.
Non-examples.
Yeah, they're non-examples, exactly. Thompson group or Bergocci group or S infinity, infinite. K A gamma, supremum over the projective dimension of those modules that have finite projective dimension. G. Make it look like a fixed point thing. Oh, such that this guy, such that my M's have finite projective dimension over all finite subgroups. If gamma is of type phi, the Taylor definition, then it is easy to show that it is equivalent, type phiness is equivalent to this quantity being finite. So these two guys are the same, and these four guys are the 1, 2, 3, 4. These four guys are the same, and they're bounded this side by theta and this side by theta plus the global dimension. As it happens, this was 21. I wrote this paper I was writing this paper in 20. In autumn 20, Manuel and Torelli had a proof of just this for Z for LHF. So this time I was able to beat them by a few months. And not only this, let's add one more sentence. Sure. Okay. Not only this, another reason why this module was effective was because David Benson in the 90s put a closed module category structure on the module category, and then the cofibrants in this structure were exactly those modules. These were the cofibrants. And it was a conjecture for a long time, well, it is still open conjecture, that this class of cofibrants should be exactly equal to the class of Goranson projectives. And it is also a theorem of mine that happens for LHF5 groups. And this is a huge class. The only groups that are known to live outside are like very few groups. This was proved before by Taleli and Fotini Dempegiotti for LHF, and A was Z. This is the exactly class of Goranson projectives. Yeah. So this is why you can see all of these invariants are linked to each other. And they are linked to the question of like their finiteness is linked to the good behavior of the category, of this category, A gamma. And in place of A gamma there, one can put a co-commutative Hopf-Algebra with some extra conditions and then try to stratify it. And that has been done for finite groups, for infinite groups, it is still open.
How about non-commutative Hopf-Algebra?
I don't know. Yeah. It is probably, I don't think it's an artifact of the proof. Yeah, I'm not so sure. Because a lot depends on these, on that map between the localizing tensor ideas and the subsets of the Balmer spectrum. And they're all defined reasonably well for co-commutative Hopf-Algebras, for stable categories of finite dimensional modules over co-commutative Hopf-Algebras. I'm not so sure what happens for non-co-commutative.
Can you have wait a second. Okay. It can be also the universal enveloping Hopf-Algebra, Lie algebra. I'm thinking what are examples of co-commutative Hopf-Algebras which are not plus rings. Yeah. But
Did I say anything wrong? Just 1 second.
yeah, well, when it's co-commutative, it's kind of like the
So this is the property of the category of modules.
Yes, it is
Symmetric. Comodules are symmetric.
Yeah.
Comodules are symmetric.
Wait, I mean, it's still a symmetric monoidal. No, it's not a symmetric monoidal category, I don't think. It doesn't have to be symmetric.
It's co-commutative. The modules should be symmetric.
Yeah. No, yeah, that makes sense. Yeah. Because the Balmer spectrum then is just the normal Balmer spectrum, what is called like the commutative Balmer spectrum. Yeah. Let me just 1 So I don't want to write anything. I mean, technically I'm done with the talk, but I want to make sure I don't do anything wrong because the result for gproj A underbar gproj underbar AG being stratified, that is quite new. Yeah, it's a finite co-commutative Hopf-R algebra, and R is a regular commutative. Those cases, they prove the stratification there.
So the tensor ideals behave like in commutative algebra.
Exactly. Yeah. That's in a way at the very core and essence of the stratification project. Yeah. Okay.
Would you put instead of a group ring, you'd put the universal enveloping of algebra, a Lie algebra? Would you be able to express some of these things in terms of a Lie algebra structure?
So these kinds of things go out the window. They are very group dependent, I think. This also. For this, probably one can do it. Because these invariants. But the thing is, I mean, in those situations, are these invariants even interesting? I don't know, because these invariants are mostly interesting because of their connection with complete resolutions and complete cohomology, I would think. Yeah, I don't know.
So can you relate this invariance with representation theory?
What kind of, I mean, for me,
What kind of representation? Because it's about this projective tails of these infinite resolutions. So what kind of problem from representation theory could be solved using this technique?
Well, I mean, representation, there was one theorem I had that was going the other way, but still similar. So for representation theory of, let's say, Artin algebras, there is an open question whether fin-dim of an Artin algebra is always finite. And there was a theorem from 2019, again, it was archive 2018, the talks were happening in 2017, which said that if you take the big Dirac unbounded category and they looked at the injective modules and considered them as complexes concentrated in 1 degree, considered in degree 0, then and if you added the condition that the smallest localizing subcategory containing the injectives was the big Dirac unbounded category, then Jeremy Ricard showed for finite dimensional algebras that it followed that the big finite dimension is finite. I could show in this case that if this is finite, if the big finite dimension is finite, then the opposite happens, as in the derived unbounded category is generated by the injectives, it's opposite direction. Now, the question of the reason I'm giving this answer in answer to saying this in answer to the question you asked is because the question of injective generation of the derived unbounded category is very much a representation theoretic property, because it has been known that when that happens, quite a lot of the so-called homological conjectures are satisfied, like the Nunke condition is satisfied and some other things. But if you're talking just about like examples of modules, like just modules for the group algebras, I'm not so sure, like in most cases with some work, or in some cases without too much work, one can prove that everything is well behaved. Like I have a project ongoing to show this conjecture. I showed it here, it is being proof LHFI. I have an ongoing project to show that this is satisfied for Thomson's group, like separately using like some cohomological information about Thomson's group. So if I had gotten that it wasn't satisfied there, then I would have had situations where there are some, okay, of course, for Thomson's group, there are some modules that are coincident, but we will have got a situation where there would have been a coincident projective module that wasn't cofibrant, and that would have had like a very nice, that would have looked very nice. But I don't know, what kind of representation theoretic applications do you have in mind?
Some asymptotic properties or something, I don't know.
Asymptotic properties, okay. Yeah, that I don't know. Yeah. Yeah, that I don't know.
Okay, so shall we wrap it up? Okay, thank you so much. All right, any further questions? I don't see anybody on Zoom. How about the room?
I would have one other question.
For the
Uh,
surprise.
would be profitable to expand this theory of the rise categories to DG categories or A infinity categories?
Hmm.
Because
I mean, this is not a-
resolution based.
Yeah, I understand, I understand. But this is not a direct category property in and of itself. Um. Not so sure. In my new paper that is not really to do with this, there is a notion of, well, there is a notion of this guy, finite district dimension, small finite district dimension, and basically one expects to look at finitely generated modules or modules that would be like, compact in some sense. For essentially small triangulate categories with a classical generator. Then we show, I mean, it's just an extension of this with the FinDim point. Then we show that there was a notion of finitistic dimension for non-positive.
Could you repeat?
There was a notion of finitistic dimension, this FinDim.
Okay.
For non-positive DG rings. And we show that our notion, our definition recovers that definition. But the usefulness of our definition is we were able to generalize a big theorem of Amnon-Niemann about the existence of bounded T structures implying regularity for schemes to general triangulate categories. And so our theorem now says if a triangulate category has a finite finitistic dimension, in a sense, and the existence of a bounded T structure implies that it has to be equal to its completion, which is also a Niemann term, and you put a Cauchy, you put a good metric on an essentially small category, construct some Cauchy sequences, and you complete the category with respect to these Cauchy sequences. So that's, in a way, one could say an extension of this to more abstract settings, wherever one can define the finitistic dimension quantity, but that is still hinging on the finitistic dimension quantity. One can go the other direction of generalization by replacing commutative rings with ring spectra. That is possible. That is possible. One can.
What about this omega factor is related to this loop?
To
Structure of the omega spectrum?
that I don't know. It is probably related. Yeah, that I not.
The notation is.
Yeah. I mean, I grew up with group cohomology textbooks using that notation. So for me, that notation comes from group cohomology, but maybe it came simultaneously. So, yeah. Anyway, one can do many of these things for connective E1 rings that are regular. So regularity replaces the global dimension finite condition there. But yeah.
So E means that you're extending these commutative rings.
Yeah, exactly. So it was forbidden in the seminar.
It was forbidden.
I mean, it was a commutative, something commutative.
Oh, yeah.
It's about a new brave commutative algebra.
Yeah. Anyway, no, that's. Yeah.
The only source of non-commutativity comes from the group structure.
Exactly, yeah. Because I mean, and as I'm saying, like if I thought I would write much more quickly, then would have got to the certification part and share one of my theorems there, which can be stated in general for this G Progender bar Hopf-Algebra thing. But yeah. I got the hang of it eventually, I think. Initially, I was not writing correctly.
Okay, so
Sorry.
what is a take-home message? I mean, why at all do people, including you, bother to study such things? Because
Invariants?
you didn't first. I apologize for putting it so bluntly, but for me, your title is false advertising because you said Hopf-Algebra invariants, and when there was no Hopf-Algebra.
No, because Goodrich-Lundberg introduced them as Hopf-Algebra invariants, introduced them for rings, but the condition, the self-split condition. The self-split condition was originally established for Hopf-Algebras.
But why did you just speak about this?
No, because I can do this generalization in this form for group algebras, scale group algebras, and strongly G-graded.
Fine, but this introduction for Hopf-Algebras this is what I wanted to.
Yeah, I think in that sense, I'll have to concede. Then in that sense, that sentence is not doing justice to the content. Yeah, in that sense.
But the notion was established
Yeah,
in the full generality.
Yeah.
But the results can be obtained for
Yeah, I mean, I can see it. That-
Classes of algebras.
Okay, for classes.
Yeah, I mean, if you only take a commutative,
Yeah,
it's a bit of an overstatement to say Hopf-Algebras.
yeah. I mean, what I said in the title is misleading, yes, but the abstract is fine because Goodrich-Grunberg did show that result for Hopf-Algebras. For K-projective Hopf-Algebras.
Mhm.
But again, for which Hopf-Algebras? All Hopf-Algebras?
No, so let's see.
Because it's just co-commutative, it's not exactly.
No. Co-commutativity was not there in the
Okay, so this is what I wanted.
in the Goodrich-Grunberg. Co-commutative is only making an appearance when I'm talking about stratification. Yes. And that is because of the support transfer.
Okay, but still my question stands.
Why did I say Hopf-Algebra?
Why do people bother to study these things? What kind of problems do you solve with this technology?
No, the problems that we are solving is extending the stratification project that has been done for finite groups, infinite groups.
Okay.
And to extend the,
And what exactly mean by stratification?
yes, so stratification means I take a tensor triangulated category T and I look at the Balmer spectrum of the compacts TC. Stratification means I should have a bijection between the localizing tensor ideals of T and subsets of the Balmer spectrum of TC. And in this one way, it's given by a very nice support map. It is being generalized more and more like every passing day.
So in a sense, you are using the idea from algebraic geometry. This Balmer spectrum.
Balmer spectrum, I mean, when Paul Balmer first introduced it, it was for any tensor triangle.
Used for reconstructing schemes, for instance.
Essentially, yeah, but like, as you know, like soon afterwards, there were so many other applications in,
Yes, of course.
in homotopy theory.
But technically, this assuming this commutativity,
Yeah.
okay, is that you are speaking about the geometric theory.
It is a geometric
Right.
theory, yes, but essentially, yes. The
Is this part the geometry which can be seen through the lenses of homological algebra?
I mean, yeah, for me, I would say in this setup, when T is the stable module category infinite group or of a finite group, then all of the treatment is done homologically. And so I'll just have to maybe cite, no, I'll have to cite Benson, Younger, Krause as opposed to like Barthel, Hart, Sanders. And if you look at the Benson, Younger, Krause annals paper on stratification of stable module categories of finite groups, all of the treatment is just homological algebra. But yes, there is a bit of commutative algebra as well, because the base string is I mean, in that case, a field. No, but let me finish my answer to your question, Peter. So yes, essentially the Matza-Simons construction of the stable module category gives a way of constructing a stable module category for an infinite group. And then one can ask, when is this construction possible? And to answer that question, all these invariants that the Greek cohomology school, Ioannis Manuel, Fotinikon Vigiotti, Olympia Deleli, and others study become important. And so it becomes important to know how exactly are they related. Are we somehow stating superfluous conditions in some cases in the assumptions? Or I mean, how much can we streamline our assumptions essentially? Yeah. So that's how it comes up.
Okay, so let's thank our speaker again.
Do I erase?